Okay, we're live.
Shall we get going? All right. Good afternoon, everyone, and welcome. It is Monday at 4:30 p.m. Eastern Time, and we are starting the second press conference of WAS 237, Exoplanets and Brown Dwarfs. My name is Susanna Kohler. I'm the editor of WAS Nova, and I will be your MC for this press conference. And I'm being assisted here today by Rick Feinberg, who's the press officer of WAS, and WAS Media Fellow, Ciardi Conchati, and Astrobytes Media intern, Haley Wall, is also here helping. So they're going to be monitoring the Slack channel, the Q&A, and checking for technical problems as they come up. So we are going to be getting started here shortly. We've got press releases for each of the talks that are being presented here in this session. So those will be posted on the AAS.org under Astronomy in the News, that section, and they'll also be tweeted out from the WAS Press Twitter account. The recording right now is, this session is being recorded, and that's being broadcast to YouTube. And these recordings will be available in the future, posted online in the press kit. So the way this is going to work is I will go ahead and give a brief introduction to the topic and to our panelists. And then each of the panelists will speak in order. And then we're going to go to the Q&A session. So if you have any questions along the way, go ahead and enter them into the Q&A section of your Zoom window. And then we're going to save those up until the end for the Q&A section. So we will not be having the panelists trying to respond to those in real time. That way we make sure that the folks who are watching this as a recording can hear and see the questions as well. We will also have a chat channel open in the Slack system. That's just for you guys to talk amongst yourselves. Please direct any questions to the Q&A session here in the Zoom window instead. So I think that's everything. Oh, last note, when you do ask a question, please make sure to identify yourself and your affiliation especially, and identify who you're asking the question of. Okay, so with that, I'm going to go ahead and get started here. We're going to be talking today about exoplanets and brown dwarfs. As Rick mentioned this morning, we have one of these sessions at every press conference, at least one. This meeting, you only get the one, so soak it up for the next hour. Although I think there's probably at least one talk snuck into a different press conference about brown dwarfs later. So our speakers today, first up, we're going to have David Ciardi from the California Institute of Technology. He will be presenting, at last, confirmation of Kepler's second planetary candidate. Then we're going to have Paul Dalba from University of California, Riverside. And he's going to be talking to us about the first results of the Giant Outer Transiting Exoplanet Mass Survey, which has the fabulous acronym Gotham. Then Lauren Weiss from the University of Hawaii, Manoa, will be presenting the discovery of a rocky planet and its siblings from the dawn of the Milky Way galaxy. And last up, we're going to have Travis Berger, also from the University of Hawaii, Manoa, who's going to be telling us about planetary atmospheres being stripped over billions of years. So I'm going to go ahead and turn it over now to our first speaker, David. And the rest of us will mute ourselves.
Okay, can you all hear me? Somebody hear me? Anybody hear me?
Yeah, we all just muted,
Yeah.
so.
Okay. Okay, I'm not sharing my screen, sorry. There we go. Can you guys all see that now?
Yes.
All right, excellent. Good afternoon, everybody, and thank you for coming. My name is David Ciardi, and I'm at the NASA Exoplanet Science Institute, which is at Caltech, and I'd like to talk to you today about confirming Kepler's second planetary candidate, finally, after all these years. So I'd like to start off actually with straight to the punchline, because I think it'll help understand the motivation for doing the system and actually why it's taken so long to do this. And that is that it's turned out that the The second planetary candidate discovered by Kepler, KOI-5, is in a triple star system. And so the planet orbits the primary star. There's a nearly equal mass secondary star, which is in a 30-year orbit around the primary. And then there's an outer star in a 400-year orbit. And so part of the reason that this is scientifically of interest is that we know that nearly half of the stars in the solar neighborhood have stellar companions, but less than 10% of the known exoplanetary host systems have stellar companions. And this is a result of actually two reasons. One, we think that stellar companions may quench or change how planetary formation and evolutionary processes occur. And also, discovery and characterization studies tend to avoid multi-star systems because they're complicated and they're difficult to interpret and to deal with. And so as a result, there's actually very little known about the properties of planetary systems when you compare single versus multi-star systems. And so this presentation is an abbreviated story of KOI-5. It was an early Kepler candidate that we were super excited about, and it was quickly abandoned, mostly because it got complicated. So this is what we originally thought when Kepler discovered KOI-5. It was discovered in the first 10 days of the mission in 2009. The bottom curve is the light curve, clearly showing the transit as detected by Kepler. It's a very clear transit. There was no ambiguity about whether or not an event had been detected. And we initially believed this to be a Neptune-sized planet orbiting an older-like sun-like star in a 5-day orbit. And I would sort of like to remind everybody that Neptune-sized and super-Earths and even Earth-sized planets are commonly talked about now. But in 2009, there were only 5 known Neptune-sized transiting planets. And so we were very excited about this system from the very beginning. And so as part of the follow-up to every Kepler transiting object, we go and we get high resolution imaging. So this is an image as seen by Kepler of KOI-5. Each one of those pixels is 4 arcseconds across. So this image that you're looking at is about the size of the full moon. And this green square that now shows up there, we're going to zoom in on KOI-5 as was observed through the Keck Observatory high resolution imager NERC2, and you can clearly see that there's a companion star right next to the primary star. The size of this image is about 1 Kepler pixel, so Kepler would never have been able to disentangle these 2 stars. By going a little bit higher resolution using a different instrument on Gemini, we're able to zoom in to about twice the resolution, and we actually see that there's 2 companion stars. There's that first one, which I now label the outer tertiary star, but now there's this inner secondary star that's right next to the primary star. So Kepler, or KOI-5, is actually a system of 3 stars. During the follow-up, we also tried to get radial velocities of the planet orbit in order to map out the orbit and mass of the planet. However, the radial velocities were completely dominated by the detection of that interstellar companion. And so we weren't able to match up very easily the radial velocities with the planetary orbit. And in addition, because we had discovered that there were 3 stars in total in the system, and the fact that there were thousands of other Kepler planets, Kepler candidates to follow up, KOI was mostly left abandoned and left unconfirmed for a decade. And then TESS came along. Well, it turns out that TESS observed part of the Kepler field, and 10 years later, TESS saw the exact same transit event that Kepler saw. This bottom light curve shows the observations as seen by TESS. The light curve doesn't look nearly as nice as the Kepler light curve, but it's only because the TESS telescopes are smaller than the Kepler telescope, but it clearly detected the transit event. And so this made me think, why did we never go back and confirm KOI-5? And so I did this detective work showing all of that high resolution imaging and showing the radial velocities. And I realized that we had just gotten distracted by all the other Kepler systems, and that the stellar companions indeed were actually too far away in orbit from the primary star to be responsible for the transits, and that there had to be a 4th body in the system, causing those transits. Now, was that fourth body a star? Was that fourth body a brown dwarf? Was that fourth body a planet? That was yet to be done, and that was the work that's new here. And so what we've done is we've combined radial velocities that had been taken of the system with actually multiple imaging observations that detected the movement of that second inner star. And so we're able to combine the radial velocities and the imaging data to solve for the orbit of that second star. And it turns out that that second star is nearly equal in mass as the primary star, and that the orbit is nearly face-on the sky and takes about 29 years to complete. Well, we then take those observations and that model, and we subtract off the motion of the secondary star, and what we're left with is that after subtraction of the orbit for the secondary star, that the radial velocities reveal the planet. And sure enough, we're actually able to confirm that not only is the planet around the primary star, but the planet has a mass of about 57 Earth masses, or about 60% the mass of Saturn. And one final part of this system, which is of interest, is that the orbits of the planet and the stars are actually not aligned with each other. We know that the planet orbit has to be nearly edge on to our line of sight because it's a transit. Otherwise, we wouldn't see the transit in front of the star. However, based on the imaging data, we know that the stellar orbit is nearly face-on. And so the orbits of the planet and the stars are actually not aligned with each other. And so this raises questions. Did the stars and the planets form from different disky material? Was there dynamical interactions that produced the current configuration that we see? And did the stellar companion push the planet into its current orbit? And so in conclusion, I just want to say that we finally, after a decade of work, have confirmed Kepler's second candidate, and that it resides in a triple star system, and that the planet is about the mass of Saturn, although it's a little bit smaller, and that the orbits between the stars and the planets are not aligned. And then finally, I just really want to say that this scientific detective work was a lot of fun, but it was made possible by the fact that the Kepler and TESS programs and the community were willingly able to share their observations and data and thoughts. Thank you. So I'm going to stop sharing if I can. Oh, it's already taken away.
Okay, I suppose that then comes to me. So I'm going to go ahead and share my screen here. All righty. Okay. So once again, my name is Paul Dalba. I'm an NSF Astronomy and Astrophysics postdoctoral fellow at the University of California in Riverside. And thank you so much for being here today. It's my pleasure to speak to you about my work, which is the Gotham Survey. And Gotham Survey is all about giant exoplanets. But at the core of the Gotham Survey is also a second goal, which is really trying to connect the parameter space between exoplanets and the giant planets that are in our own solar system, because there's a bit of a discrepancy. And to explain that, I'll show this image here. Now, this is an image of all of the orbits of all known exoplanets as if those planets orbited the same star. And it's a bit messy because we know of a lot of exoplanets so far. So each little fuzzy dot and each little white line is the orbit of an individual exoplanet system. Now, most, or I should say about 50% of the known exoplanet systems to date fit within that white dashed circle that I'm showing right in the middle of the image right there. Over 2,100 exoplanet systems. And then if we move out to the orbit of Mercury, about 80% of the known exoplanet systems would fall within that orbit. So what I'm getting at is that most of the exoplanets that we know of are very, very close to their host star. And in fact, as we move further and further away from the host star, the amount of information we know about the exoplanets is less and less. The problem is even more severe if we actually step further out, we zoom further out in this image, to the scale of the giant planets in the solar system. Now, instead of all that messiness, you can actually count the individual orbits here and the individual planets. And so part of the Gotham Survey is really trying to fill that gap in between the very, very short orbital period of known exoplanets and the longer period planets of the solar system. Now, a little more specifically with the Gotham Survey, we can break down the goals by breaking down the words in the acronym. So first and foremost, this is a giant exoplanet mass survey. And the focus on mass is due to the fact that masses are one piece of the puzzle of understanding how planets form, how planets reach their current orbits, because giant planets tend to like to migrate from their starting position. And also how giant planets affect other smaller, possibly terrestrial-sized planets during that migration. So giant exoplanet mass surveys have been done to great success on exoplanets, and they have focused on planets that are very close to their host star on the order of 1/10 of an AU, AU being the distance between the Earth and the Sun, all the way out to about 10 AU, which is about the orbital distance of the giant planets in the solar system. But the key for the Gotham survey is that T. It's T for transiting. So we focus on planets that cross in front of their host star from our point of view, creating a transit. And the important factor there is that when the transit occurs, we can measure how big the planet is in addition to just its mass. So with masses and radii, we can complete the puzzle of how planetary systems form and what those planets are likely made of. And for transiting giant exoplanet mass surveys, the focus has mostly just been on those that are very, very close to their host star on the order of 1/10 of an AU. There are some transiting giant exoplanets out at about 1 AU. They're just very difficult to characterize. And those were the difficulties that the Gotham survey tried to confront. And so that, of course, brings us to the outer aspect here. So the focus is on planets that are at intermediate long periods in between the known exoplanets and the giant planets of the solar system. They're stepping stones, if you'd like. And the main question at the core of all of this is, do giant outer planets form or migrate differently than those that are much closer or much further from their host stars? So it's been a couple years working. Long periods means long projects. So I'm very pleased to announce we finally have results for our first system, and it's Kepler 1514b. Now, this was observed by the Kepler spacecraft. I'm showing the transit light curve here. And based on those observations of transits, we found that the orbital period of this planet was 218 days, which put it at about 0.8 AU from its star. And this transit light curve is just magnificent. And from it, we were able to very precisely measure that the size of this planet is about 10% larger than Jupiter. So pretty similar to Jupiter. And the temperature of this planet is about 390 Kelvin, which is like 240 degrees Fahrenheit. Now, relative to Jupiter, which is around 100 Kelvin or so, that's still pretty warm. But relative to almost all other giant exoplanets that are transiting and have had these kind of measurements, they're on the order of thousands of Kelvin. So this is a sufficiently cool planet. But the main question here is, how massive is it? Recall, we want to get the radius and the mass to put those together to try to tell the full story. So to answer the question of how massive is it, my team and I went to the Keck 1 telescope at WM Keck Observatory on Mauna Kea, and we measured the wobble of the host star that's induced by the gravitational pull of the planet. So as the planet orbits, the star also orbits the common center of mass of the system, as is being shown here in this video. So by taking observations of that wobble, we were able to back out how massive Kepler 1514b actually is. So the data points that we acquired from Keck Observatory are the white diamonds, and the model we fit to that is the model of the wobble, I should say, is the red line. And based on that, we were able to find that this planet is about 5.3 times more massive than Jupiter, despite the fact that it's only about 10% larger than Jupiter. Now, in addition to the mass, critical piece of information here is the orbital eccentricity, which is really how circular or how elliptical the orbit is. Now, a circular orbit has an eccentricity of 0. Jupiter's eccentricity is about 0.05, so pretty circular, but the eccentricity of this planet is 0.4, and we know that pretty precisely too. So that's a key piece of information in putting together the story of this system. So with all this information, what did we really learn? So the first and foremost thing we learned is that Kepler 1514b is a very dense planet. Here I'm showing it to scale with Jupiter as far as size goes, but Kepler 15b is 5 times more massive. And putting together size and mass gives you bulk density. And relative to Jupiter, this planet is almost 4 times more dense. And relative to Saturn, it's over 7 times more dense. And even relative to other outer giant exoplanets that have had these types of measurements, it's in the 95th percentile of bulk density. So it's just a dense planet. And these findings are going to motivate future studies that try to explore what the interior properties are of the system, specifically how heavy elements like metals are arranged inside that planet, and how that might help us understand how Jupiter and Saturn are arranged in their interiors as well. But I'll lastly just revisit this idea of orbital eccentricity, because this property provides clues to how planets migrate. So for giant planets that are around this orbital scale, they're left with some orbital eccentricity, it's thought that that's a remnant from their formation. And so one theory to explain how this planet got this eccentricity is that it underwent some sort of planet-planet scattering earlier on in its formation. That means there may have been another planet that it had a gravitational interaction with that was scattered, and then Kepler 1514b survives with this eccentricity. However, there's something I haven't told you about this system, and that's that there's an additional planet, Kepler 1514c, and I'm showing the orbits of these two planets to scale here in this video. Now, Kepler 1514c is smaller. It's about the size of the Earth, maybe a little larger. We weren't able to measure its mass because its gravitational tug on the star is too small. But just the fact that it exists perhaps casts doubt on the fact that there was an episode of planet-planet scattering. So future observations are probably needed to really dial in and finish the story for this system. But my concluding point here is that more mass and orbital measurements of planets like this system, which is the goal of the Gotham Survey, are really going to place these planets in context of the hottest Jupiters we know and the cold Jupiter that's here on our own system. So I'd just like to say a couple acknowledgements very quickly. First and foremost, of the observations that we took at Mauna Kea, we are deeply grateful for the opportunity to make observations on that mountain. And I'd also like to acknowledge my collaborators, and specifically the collaborations I work with the California Planet Search and the Tescac Survey that really enable that important RV cadence that was acquired for this system. So please check out the paper. It's now accepted to the Astronomical Journal, and thank you. And I'll pass it off.
You're muted, Lauren.
Almost had everything. Aloha. My name is Lauren Weiss, and I'm the Parent Postdoctoral Fellow at the University of Hawaii at Manoa. Today, I'm presenting a discovery of a rocky planet and its siblings that have existed since the dawn of the Milky Way galaxy. The planet, called TOI 561b, is one of the oldest rocky planets yet discovered. This planet formed at a time when the majority of stars in our galaxy were first beginning to shine. And its existence shows that the universe has been creating rocky planets almost since its inception 14 billion years ago. Our discovery is part of a NASA Keck strategic mission called the Tescac Survey. This project is run by a multi-institutional team, of which I'm a co-investigator. Our survey is supporting and enhancing the NASA TESS mission, an ongoing space mission that is searching for planets around the nearest stars. The Tescac Survey goals are to confirm the existence of the small planet candidates discovered by TESS, and to measure their masses using the W.M. Keck Observatory on Mauna Kea on the island of Hawaii. The TESS data indicate a small planet orbiting the star every 0.45 days, what we call an ultra-short period planet. Every time the planet crosses between the star and the telescope, it blocks a small fraction of starlight, diminishing the apparent brightness of the star. This plot of the star's brightness during each of 55 transits shows just a very small dip. I apologize to the journalists who are straining their eyes to see this, but these transits are incredibly difficult to detect. The planet blocks only 0.025% of the starlight, which corresponds to a planet with a size of 1.5 times the radius of the Earth. You might be wondering, with such a tiny dip, can we trust that the planet is really there? With the Tescac Survey, we have obtained data that confirm the orbit of the planet and reveal its mass. We have measured the stellar reflex motion that corresponds to the gravitational tug of the planet on the same orbit as what we determined from the transit data. This plot is showing the motion of the star over the entire orbit of the planet. The characteristic up-down curvature is exactly what we expect from a real planet. The amplitude of the star's motion indicates that the planet is about 3 times the mass of Earth. we can gain insight into the interior makeup of this ultra-short period planet by comparing its size and density to those of other small planets. Other published exoplanets are shown in gray on this plot, and the planets of the solar system are labeled in white boxes. The lines of various solidness and dashed and dottedness all correspond to theoretical models for planets of various compositions. TOI 561b is consistent with having a rocky composition. At an orbital period of 0.45 days, it is very close to the star with an average surface temperature of 2,500 Kelvin. At this temperature, we expect the planet to have formed a magma ocean spanning the entire hemisphere of the planet that faces the bright star. The star has at least 2 additional transiting planets, which are larger and lower density than the rocky planet, indicating that they have thick gaseous envelopes. The biggest surprise of our investigation was that the planetary system orbits a star in the Milky Way's sparsely populated, ancient, thick disk. This graphic shows an artist's conception of how our Milky Way galaxy would look if we could view it edge on from a great distance. The Earth and almost all of the 4,000 other planets that we know of orbit stars in the thin disk, which is outlined in the very elongated light orange oval. But TOI 561, our star, belongs to the galactic thick disk, which is outlined in the larger red oval. Stars in the galactic thick disk have motions that take them high above and far below the plane of the galaxy, providing them with what might be stunning views if anyone were there to see them. The way we discovered that the star belongs to our galaxy's thick disk was through its unusual chemistry, which we measured in the data we collected from Keck. This plot is showing the abundances of metals, both iron and non-iron metals, in thousands of stars, including some with planets. The stars separate into 2 groups, which are divided by the dashed line. Stars below the line, which include the sun, belong to our galaxy's thin disk. Stars above the line, including TOI 561, belong to the galactic thick disk. The chemistry of each star is linked to its age. The sun is 4.5 billion years old, whereas TOI 561 and its planets are 10 billion years old. For comparison, our Milky Way galaxy is 12 billion years old, barely older than this particular rocky planet and its system, and the universe as a whole is 14 billion years old. In summary, we've discovered a rocky planet and its siblings from the dawn of our Milky Way galaxy. The star TOI 561 hosts a rock and magma planet and at least 2 gas-enveloped planets, all of which were detected by the NASA TESS mission and confirmed by the Tescac Survey. The star belongs to the galactic thick disk, which is a chemically unusual population of stars that are about 10 billion years old. TOI 561b is the first planet with a confirmed rocky composition around such an old star, demonstrating that rocky planets have been forming for most of the history of the universe. I just wonder if any of them have anyone we'd like to talk to. Thank you, mahalo.
Okay, hi everyone. My name is Travis Berger, and I'm a graduate student at the Institute for Astronomy at the University of Hawaii at Manoa. and today I'm excited to tell you about how planet atmospheres are stripped over billions of years. And this is work that I've been able to complete with the help of collaborators Dan Huber, Eric Gaidos, Jennifer Van Saders, Lauren Weiss, and Jamie Tyar. So for those of you who are not familiar, the main goal of the Kepler Space Telescope was to detect Earth-like planets around Sun-like stars. And to do that, the Kepler Space Telescope stared at this one portion of the sky for roughly 4 years. As you can see, it's just outside of the constellation of Cygnus. And Kepler ended up viewing this for 4 years straight with the main goal of detecting transits around these stars that you can see on the CCD here. This is the Kepler Detector. And as you can see, there are hundreds of thousands of stars. And so as we've heard about a little bit earlier, Kepler's main goal was to detect these dips in the light from those stars over time. And the size of those dips actually give us information about how large the planet is relative to the size of the host star. Now, as of 2018, Kepler had detected roughly over 2,600 planets. Now, to kind of give you all an idea of exactly what these planets look like, here are the Exoplanet Discoveries as of December 14th, 2017. Kepler at this point had discovered just over 2,500 planets, and you can see them in yellow here. On this plot, we've got the size of the planets relative to Earth on the y-axis versus how long it takes those planets to orbit their host stars on the x-axis. And you can see that the vast majority of these planets are between the size of Earth and Neptune. Now, this is particularly interesting for us astronomers because we don't have any planets within our own solar system that are between the size of Earth and Neptune. So what exactly is going on with these planets? So it turns out that based on all the work that's been done over the past decade or so, that these planets can be separated into super-Earths and sub-Neptunes. Now, super-Earths, as their name suggests, are similar to the Earth, but slightly larger. So they can be anywhere from 1 to about 1.8 or so times the radius of the Earth. Whereas sub-Neptunes are slightly larger planets, usually anywhere between 1.8 to about 3.5 times the size of the Earth. And this extra size is usually made up of additional atmosphere of that planet. And as the name suggests, these sorts of planets are actually just smaller versions of what we see in our own solar system in Neptune and Uranus. And so therefore, we've got these two different types of planets which occur in this kind of range of sizes between the size of Earth and Neptune. Now, going back, we've got all this interesting planetary data, but as of 2018 or so, we lacked distances to the majority of Kepler stars. Now, you're probably wondering why is that a problem? Well, it turns out that without distances, it is very difficult to tell the difference between 1, a large star that is far away, and 2, a small star that is very close by. Now, you can start to see where this could cause some problems in terms of how we determine the sizes of planets, because we are measuring planet sizes relative to the size of the star with the transit method. So luckily, this is where Gaia DR2 comes in. And so Gaia ended up mapping the Milky Way galaxy. And this is just an image from the Gaia data. But with Gaia, it measured something called parallax, which is essentially what your eyes use to measure the distances to objects, or what gives you depth perception. And so thanks to Gaia DR2 parallaxes, on astronomical scales, we can now infer the distances to most of the Kepler stars. And so with this distance information, this then allows us to constrain how large the stars are. So to give you all an idea of exactly where things were before Gaia DR2, here is a plot of stellar size relative to the sun on the y-axis versus stellar surface temperature increasing from right to left actually here on the x-axis. And you can see, so if you're wondering where the sun is located, it's right about where my pointer is right now. And you'll notice that there is some weird banding going on here. The distribution isn't very smooth. So what happens when we implement Gaia-DR2 distances to constrain the sizes of stars? Well, we see that things sharpen up very nicely here. And something additionally that we can get out of these updated sizes is that they allow us to actually constrain stellar ages as well, because it turns out that the location of a star on this diagram gives us information about how old that star is. So given that we've got all of this information, we've got the updated planet sizes, and we have these brand new stellar ages, what is it that we can learn about how planets vary with stellar age? So here we've got number of planets on the y-axis versus planet size relative to Earth on the x-axis. The Earth is located right here at about 1. That's an Earth-sized planet. And we increase from left to right here. And this is a distribution of the old planets, which are roughly older than about 1 billion years old. Now, what's really nice in this plot is we can actually see the distributions and the populations of super-Earths and sub-Neptunes as these two peaks that you can see here. And these super-Earths are anywhere from about 1 to about 1.8 or so times the size of the Earth, and the sub-Neptunes from 1.8 to about 3.5 times the size of the Earth. And what we also want to know here is how these planets might evolve. So what do the young planets look like? Well, we see that there's a significant difference between this overlaid green histogram and the purple histogram underneath. In particular, you'll notice that the super-Earth peak in this green histogram is significantly lower than what we see in the old planet histogram. And for the sub-Neptune peak, it is significantly broader than what we see in the old planet histogram and shifted to slightly larger radii. So given all of that information, what is it that we can say about sub-Neptunes? Well, I think what we could say is sub-Neptunes shrink and are stripped over these roughly billion-year or so timescales. And so to just sum everything up here, you start off with a sub-Neptune, you hit it with a bunch of high energy radiation and lots of it over billions of years, and eventually you can strip off its atmosphere and make it become a super-Earth. And this suggests that there is an evolutionary pathway leading from these sub-Neptunes to super-Earths. Now, if you don't receive as much high illumination, you could end up getting a slightly smaller sub-Neptune over time. But overall, this is the major result here. And so I thank you all for your time, and I look forward to taking any of your questions. Thank you.
Fantastic. Thank you so much to all of our speakers. We'll go ahead and go right into the question session.
Right, yeah, we do have a couple of questions in the chat. This first question comes from Jennifer Wiseman, and it's directed at Paul. Could you speculate on whether these planets have habitable moons?
Yes. All right. Thank you. Good question. I've thought about this a little bit, just with the kind of excitement of we haven't found any exomoons so far, and we've perhaps been looking around planets that are not the best host for them if they're too short period, too close to their host stars in a gravitational environment where it's not likely that moons could survive. So pushing out to giant planets that are further away maybe is a great place to look, like this planet. So we don't have any evidence right now as to whether or not this system has moons. So but I can speculate, as you suggested. Something interesting about this planet is that it had the transits that were observed by Kepler showed transit timing variations. So little changes in when the transit occurred based on when we expected it, if it was just a planet and the star entirely alone. Now, those were of weak statistical significance, so we can't make too much of those. But one possible explanation for those is an exomoon causing that kind of interaction. There are other possible explanations. However, given that we now know the mass of this planet and we are now starting to learn more about how it might have formed, I think it's worth revisiting to search for. I should say one perhaps reason against the existence of an exomoon is if this planet did undergo a scattering event previously, that's something that an exomoon may not have been able to survive. But to get to the end part of the question, is it a habitable moon? the temperature, the equilibrium temperature, which is sort of a balance of the energy in and out of the planet, is about 390 Kelvin, which is 240 degrees Fahrenheit. So it's probably too hot for it to be habitable on the surface with an atmosphere with liquid water. Whether or not it could be habitable within the moon would be a whole nother question. So I think it may be very possible this has moons, but I think they're likely not habitable.
Thank you. This next question comes from Monica Young of Sky and Telescope, and it's directed at Lauren. Surface lava on Earth, if I recall correctly, is hotter than 2500 Kelvin. Is there any way to model what kind of magma/rock could be on this planet?
Yeah, that's a great question. So actually a problem is that a lot of these exoplanets have day-side temperatures, so expected temperatures where the star is shining right on them that exceed the temperatures at which geophysicists have made magma in the laboratory. So these temperatures actually exceed sort of the magma and lava systems that we see on Earth. But there are some people who work on the theory of heat distribution in these planets, and it's actually their work that has inspired me to speculate that perhaps there's a magma ocean on the side facing the star. And then on the dark side, the night side, where there's not radiation from the star heating the planet, that could be cool enough to be rock, potentially. We don't know though. We haven't actually observed the magma or the hard rock, right? This is just based on our best understanding of how physics works.
Thank you. This next question comes from Govert Schilling, freelance, also directed at Lauren. We've always been told that Earth-like planets could only form late in the evolution of the universe, when enough heavy elements were formed by stellar nucleosynthesis. Does this discovery refute this argument? And also, does it imply that life could also have been forming earlier than we used to think?
Yes and yes. So this is actually not the first discovery that that small and even rocky planets can form around stars that are poor in their metal content. So you rightly connected the metal poor chemistry of this star and its galactic thick disk population to the sort of the irony that the planet is rocky. So actually over the past 5 years, there's been an emerging picture that rocky planets can form around metal poor stars. And now this is the first time we've discovered a planet that we've now confirmed to be rocky around a star that's both metal poor, but also a confirmed member of the galactic thick disk. So this special population of metal poor and old stars. So in terms of what that implies, yeah, that means rocky planets have potentially been forming for the past 10 billion years, perhaps all 12 billion years of our galaxy's history. I don't know about those earliest 2 billion years, but gosh, if we've only been around for 5 billion years, imagine what could have happened on a rocky world that's been around for 10 billion years. I'd sure like to find out.
Thank you. There are no more questions in the chat, so I will hand it back to Susanna.
I actually have a question, if I might.
Only one?
Yeah, sorry. So Rick Feinberg, AAS press officer. My question is for Travis Berger. Are you suggesting that the mechanism that you've identified for whittling a sub-Neptune down into a super-Earth is the only or the predominant formation mechanism for a super-Earth, or is it just one of many possibilities?
Yeah, so I wouldn't say it's necessarily the predominant form. Right now, we don't really have a great idea of exactly what the base mass distribution of the cores of these planets are. And so one thing to keep in mind is that while that can be a way that you can form a super-Earth, there might also be other ways that you can form super-Earths, and it might also depend on the exact type of star that you're considering as well. So atmospheric, sort of stripping by radiation from the host star and energy from the host star is definitely something that can create super Earths, but I wouldn't go so far as to say that that's a dominant mechanism, but it is definitely one of them that we do have good evidence for that being at least, common.
And if I could follow up, can you remind us why there's a distinct gap between the two populations?
Yeah, so the gap between the two populations of super Earths and sub-Neptunes is mainly caused based on what these planets, their atmospheric loss timescales. So let's say you've got a population of super Earths or sub-Neptunes, and you're hitting them with a bunch of radiation. Depending on, they have kind of stable regions where they can either hold on to roughly 2 times. So the sub-Neptunes have roughly 2 times the atmosphere of a super Earth. And it turns out that that is actually a relatively stable, you're relatively stable to collapse and lose your atmosphere if you are a sub-Neptune as, above that gap. It's based on the time scales associated when these planets, they form super hot from their heat from formation. And so they start off very puffed up. And so if they're still receiving a lot of energy from their host stars, then they can end up losing that atmosphere and then they become super Earths. But if they don't receive enough energy to where they can actually be stripped of their atmospheres, then you end up with just maybe a slightly smaller sub-Neptune. And so that's where you see in the gap is where they are actually very unstable to lose their atmospheres.
We do have another question from the chat. This is again from Monica Young of Sky and Telescope, directed at Lauren. Aside from stars being metal poor, are there any other challenges for making planets early on in the universe?
Yeah, so just to elaborate and maybe clarify this a bit, it turns out that stars being metal poor is not a challenge for forming rocky planets early in the universe, not a challenge at all. And actually recent work by both Travis and another colleague of ours, Eric Pettigura, has shown that the metal poor stars are pretty much just as good at the as their metal rich friends at forming planets. So, maybe what I should talk about here is that that's a bit of a surprise, right? The reason for that is you would expect if a star has a lot of metal, iron, and also the other non-iron metals, like we astronomers think of things like silicon and magnesium as metals. If a star has a lot of those particular elements, you would expect that the disk in which it is forming and from which its planets will form would also have a lot of those metals, and that if you have a lot of those metals, maybe you do better at forming rocky planets. But that's not the case. It turns out that all the stars, sort of whatever their metal content, are pretty good at forming rocky planets. So we still don't really understand how planets form. So I think that the challenge is really our understanding of how planets form from this sort of chaotic nebular material, and then how that eventually coalesces into the nice ordered planetary systems like the one that we live in. So there's a lot of work still to be done there.
I just want to follow up on that question, Lauren, specifically focusing on what implications this has in the search for life. Mm-hmm. I mean, if it's not a challenge to form planets from a metal poor environment, and these planets have been around for much longer, giving potential life more time to evolve, is this where we should be looking?
Possibly. Yeah, actually, I think if I had to stake my bets, I would more readily bet on a 10 billion year old star and its rocky planets having some intelligent civilization than a 1 billion year old star and planets like the ones Travis showed us, which are beautiful for understanding the formation of planets, but maybe don't yet have aliens.
So what are our prospects of being able to detect more planets like this one?
That is a great question. I think our best prospect right now is the TESS extended mission. So the NASA TESS mission has been wonderful at finding nearby small planets, some of which, like the rocky planet I presented today, some of which are small enough that they're actually rocky. But as I showed you in the data with that dip from the transit, my gosh, they are really hard to find in the present data set. The way we are going to find more of those rocky planets, especially ones around the nearest stars, where, you know, if we want to go talk to aliens, we don't want to talk to aliens that are 1,000 light years away. We want to talk to the ones where maybe our grandkids or their grandkids might actually receive the message. So, so we want to be looking for rocky planets and alien civilizations that are close to home so we can have a conversation. But we've got to be better at detecting these really tiny dips from the rocky planets. And we've got to branch out as well. Only a small fraction of stars, of planets transit their stars. It has to be just aligned between the telescope and the star. So there are lots of rocky planets out there that are not transiting their stars. And we need to build the telescopes, build the ground-based telescopes, for instance, 30-meter class telescopes will be really important for discovering and characterizing these nearest rocky worlds. Future space-based missions as well. We're going to use the transit method. We're going to measure the wobbles of the stars, and eventually we will directly image these rocky planets. That is the way we have to go.
Got a few more questions in the chat. This one comes from Ross Burns, and we'll just toss it out to the whole panel. Are magnetic fields needed for retaining the atmosphere of a planet?
I can take a stab at this one. So I'm not a solar system planetary scientist, but my understanding is that Earth's magnetic field has played an important role in protecting our atmosphere. So perhaps magnetic fields are important for maintaining atmospheres. There are a couple of instances where magnetic fields have perhaps now been detected on brown dwarfs. So like huge, giant, 10 times the mass of Jupiter objects, which are not rocky worlds that you could set foot on. So it will be interesting to see if those techniques can be extended to the small rocky worlds that we would like to probe.
Thank you. This question comes from Dan Clary of Science Magazine, and it's directed at David. Can you say more about possible formation mechanisms for a 3-star system with such a misalignment of planet and stellar orbits?
Yeah, sure, of course. Thank you for the question. So one of the things to recognize is that probably the configuration that we see today is probably not the configuration in which the system formed. And that's probably true for a large number of systems, right? And one of the challenges in exoplanet astrophysics is trying to understand what we see today and how that translates into how things formed a billion years ago. So there are a variety of ways that we could get into the current configuration that we see for KY5. One is that the inner stellar companion actually formed further out from its own disk and then got kicked inwards by the outer star. And so the primary star with its planet formed in one disk, and the secondary star formed with its own disk, and then that outer star formed with its own disk. And then through the dynamical interactions, it kicked the inner star into an inner orbit. And then because that inner star moved in, then that kicked the planet into its inner orbit. It's one possibility. It's also possible that the stars formed where they are, and as a result, the planet had to form in a tilted disk. Otherwise, it would have been disrupted by the disk of that inner star. So one of the other questions that could help address this is, what's the orbit of that outer star? 400 years is a long time to get radial velocities, but that is one of the questions. But the other and perhaps more direct way of addressing that is asking, does that other inner star have its own planets? And so there's a new generation of instruments coming online which use high resolution adaptive optics to be able to put light from one star directly down the fiber, getting rid of the other star out of the way. And so the next generation of radial velocity instruments might be able to address that question directly. Does that inner star have planets? And if it does, then we can use those orbits of those planets to constrain, okay, that's probably how that system formed versus the primary star. And so it's a really excellent question, and rewinding the clock to the formation is actually quite difficult from what we see today.
Thank you. There are currently no questions in the chat.
I have one more question for Travis, actually. Looking at that histogram, it seems like your conclusions are hinging on a relatively small number of planets. Are there plans to kind of build that out in the future, hoping for an increased sample size?
Yes, absolutely. So this is kind of, so I'm currently a kind of last year grad student right now, and something that I'm potentially planning on doing from potential postdocs is looking into, taking all of the data that we have for all of the NASA transiting planet space telescopes, all of those missions, and seeing what we can get out of those. One of the great things about Kepler was being able to look at, for instance, a lot of solar type or sun-like stars, but K2 and TESS are going to be able to go, both to less massive stars and more massive stars on the main sequence. So all of that is going to be incredibly useful, plus just beefing up the numbers total. And then also potentially using other potential age determination methods that can be helpful for stars that, for instance, we weren't able to use for this result.
Right, thanks. And then I actually had one more question for Paul, kind of along the similar lines, which is, where do we stand in this Gotham survey? Have you made other similar detections? What's the projection for, filling out that space of planets we really haven't detected yet and characterized?
Yeah, thank you. That's a great question. So the Gotham survey started with a little over a dozen planet candidates, all of which came from Kepler. And Kepler was the ideal case to do this because it stared at the same patch of sky, as Travis told us, for about 4 years. And so you have to look at a lot of stars to overcome that transit bias to get the ones that are just aligned. And then you have to look at them for a long time in order to wait out the length of their orbit for the ones that do. So I had about a dozen of them that we've been working on for a couple of years. We have some really exciting ones. 218 days is actually one of the shorter period ones of the sample, which, as you might expect, would be the one that would come first. We have one that's closer to 1,000 days that's coming next, which is exciting. And I'll also add that the Gotham survey also has a Gotham TESS aspect. Although TESS looks at most of one of the benefits of TESS is that they're brighter stars, they're closer, and it looks at the whole sky. But even though TESS looks at most of the sky for a lot shorter length of time, on the order of a month rather than 4 years, occasionally you'll get lucky and you'll happen to catch one that just transited when TESS looks. And we've got 3 or 4 so far that are coming from TESS that are much brighter, much closer, and very exciting for that aspect as well. So this time next year, there's going to be a much larger sample.
That's awesome. Sounds like we're going to need to have another Exoplanets and Brown Dwarfs press conference, Rick.
It's inevitable.
Yep.
I just want to point out too that the Slack channel has been very quiet, which tells me that people have been paying rapt attention to this briefing rather than chatting among themselves, which is the way it should be.
Excellent. All right. Well, it sounds like we've hit all of the questions then, unless I'm missing something. So I just want to thank all of our speakers again for these excellent presentations. And thank you to all of you here in the audience listening today. We also want to thank the PIOs who helped the presenters get press releases together and prep for this. And we look forward to seeing you guys tomorrow for our next press conference, which will be at 12:15 p.m. Eastern Time. And this is going to be Galaxies and Quasars 1, because we've got a lot of galaxies and quasars this meeting. So see everyone then.
Thank you, everybody.
Thanks all. Bye-bye.
Thank you.